So let's start the topic. Today we are going to discuss about a new topic, and the topic's name is phenomena and the measurement of a flow rate by using a vortex flow meter. So we'll discuss about the vortex flow meter here and how it is used in measuring the flow rate of a particular liquid. Here we will discuss about it here. So let's start the topic. So basically this is a vortex flow meter, and this is the setup of a vortex flow meter, and you can just see this is a high purity design, this is a high pressure design, and this is a 12 sensor design. So here we can see that the high purity design is basically these things are the different kinds of vortex flow meter. So first of all we'll have to understand what a vortex flow meter is and what does it do. So let us first jump into the topic and how does it used in industries. Why does it used in the way we use it in the industries? We will just get to know about it in this video lecture. So first of all we'll have to get a basic knowledge about the vortex flow meter function and its process and working principle. Before going to the topic, we'll have to understand how does a vortex flow meter works and with what phenomena we can just get an analogy of the function, the processes of this vortex flow meter. So here is an example of a golf ball. Basically when you play a golf, you hit a ball. It's like cricket, you hit a ball and it is in a projectile motion, it goes to another place or another direction. So when it travels through the air, you can see when it basically travels through the air, it is going in a projectile motion, and the velocity of the ball is depending upon how hard you hit the ball. Likewise, when you hit the ball, it will go in through the air like this if its velocity is low. When the velocity is slightly higher, it will go through the air. This is the air particles. Okay, this is air particles, no disturbance in the air particles, but when you hit it hard, there is some disturbance which causes irregular eddies to form behind the ball. Now let us come to this third one. When you hit a ball with a more velocity, it goes through the air, and now you can see this is the swirls, or you can say these are basically the eddies is forming here, the eddies of the air. So likewise, this is the analogy to the formation of the eddies of the water inside the vortex flow meter, which is just used for measuring the pressure. Okay, so by measuring the pressure we can just use it for measuring ultimately the flow rate of a liquid or something in a flow meter. So that's all. This is the first example. We have another example, like this is the mountain. These are the air clouds in the air, or the mountain. Around the mountain is the clouds. So what happens, these mountains are the obstructions to these clouds, and what happens is this: when the cloud just get obstructed by these mountains, it goes in the direction, the port direction, and it forms an eddy, like an eddy in the cloud. So these eddies are basically nothing but the vortices. Okay, these eddies are the vortices, and these vortices are basically analogous to the main functioning of a vortex flow meter. So here it is another example. We have got the third one. This example is of a light breeze, like you have seen in the air when there is some kind of wind out there, and this is obstructions like a piece of a stone in the mountain. The air current flows, and this is the light breeze whose net rate is 0 to 5000. So this is the laminar flow you can see out there, but when gradually the wind rate increases, then the stiff breeze, in a kind of a stiff breeze, there is a rate increases, that is 5,000 to 20,000. We can check it out here, that here some irregularities form here, like this is the irregular vortices. And again, in a strong kind of wind, we can see this comes here again, like this, the regular vortex pattern in the turbulent wind flow. We can check it out here. Yes, these things are just nothing like different from the previous one. These are all similar kind of things, and that's all we have to get out from example from the nature. This is the examples from the nature we've got, and now we'll jump out to the principles of operation of this vortex flow meter. So basically what a vortex flow meter is, inside the vortex flow meter, if you see, you can find out this is the shaded bar assembly, this is the bluff body, this is the alternating vortices, yes, these things. This is the particularly, this is the fluid, this is the liquid. So again, from the topic, we'll start again, the principle of operation of this vortex flow meter. Yeah, so first of all we'll have to understand the principle, how does it operates and how does it functions. Again, we have to understand the definition of a vortex flow meter. So according to the definition, we can say vortex flow meter is a type of a instrument which can be used to find out a wide range of vortex flow rate in a fluid. So it can be a fluid, like it can be liquid, it can be gas, and it can be steam. So thus there are three types of fluid can be there, and it can be used in a wide range. For basically we can use it in a particular thing, in a particular flow rate where we don't want to use any movable parts, because this vortex flow meter does not contains any movable parts, because as we have seen that in previous in some cases, if there is a movable part, it causes some wear and tear in it. So just for that reason we can use vortex flow meter in that place. So as of that, they are to be seen as the first choice, subject to verification to cover the requirement of a particular applications. And again, these vortex meters are essentially, they are also known as frequency meters. What is the reason for that is, it is called frequency meters. The reason is that they measures the frequency of a vortices generated by bluff body. So basically the flow rate basically depends on the frequency of the vortices which is produced. So that's why it is also known as frequency meters. And vortex meter are actually a volume flow meter also. It measures the flow meter in a volumetric flow meters. It measures the volumetric level of a liquid, and that's why it is also known as volume flow meters. And like that of the orifice meters, it is also known as volumetric flow meters. And again, we can say that a vortex flow meter is a flow measurement device best suited for flow measurement, where the introduction of moving part present problems, as I have discussed earlier. Okay, so that's all. And the vortex flow meter operates under the vortex shading principle. We'll discuss about that also in the upcoming video lectures. So what kind of thing and the principle it depends upon is this principle. So when a flowing medium strikes a non-streamlined bluff object, it separates, as you can see in this picture, moving around the object and passes downstream. You can see at the point of contact with the object, vortex swirls, separates from the body on alternating sides. Yeah, we can see this is the alternating sides, and this is the separation causes a local increase in pressure and decrease in velocity of on the one side, and decrease in pressure and increase in velocity on the other side. Yes, like vice versa. So we can see there is a decrease in pressure, we can see, and also increase in pressure on the opposite side, and decrease in this one velocity and increase in velocity on the other side. So there is a two difference, and that's that's the measure point where we can find the difference between the two point, and from the difference we get the output, or we get the result of the basically the sensing element gets the result to find out the flow rate. So these two difference created the two sides, and that's why we can sense it by using some elements and the ending point, which will give us the final result. So the alternating velocities generated alternating pressure forces on either side of the bluff body. Yeah, the frequency of these pressure changes is proportional to the velocity. Yes, this is the main topic and the main point. The frequency, as I've discussed earlier, is directly proportional to the velocity of the vortices. So this is going to be the main formula or the main funda of this topic. The frequency is directly proportional to the velocity. Yes, this is the main funda, for which we'll get to know in the later discussions that this is the main formula for measuring the flow rate. And that's it. This is the principal operation. It's very simple. And this is the type of vortex sensors out there. So this is the type of vortex sensor. You can find it the differential switched capacitor and shutter bar. There's an integral diaphragm. There's a thermistor. So that's all. And again, we have the unique sensor design. How does it work? And we have got some unique sensor design of it, and how does it work for like I've discussed earlier. Let us again jump into the topic again. Like a flow hits the shutter bar, yes, separates, and due to the shape of the bar forms vortices. That's the shape I was talking about. This is the shape, like in the mountains you have seen. This is the shape for which the vortices are produced here. The vortex creates an alternating pressure differential across the bar. The bar is physically stressed towards the low pressure side of the bar. Yes. So basically, what it does is the vortex is created an alternating pressure difference across the bar. So there is a difference in these two vortices. There is some difference which will be sensed by a sensing element out there, and that's all. The instrument works out there, very fine, very specific, for only for the liquids. It cannot be used for a solid. That's why the bar is physically stressed towards the low pressure side of the bar. Yeah, this is the low pressure side, and the physically stressed like that in the position is like that only. So which makes the vortices of the fluid inside the pipe. This is a pipe. Generally this is a piezoelectric crystal mechanical stress, and this is the mechanical part of this particular meter. So we'll jump into that again in the next videos. The principle of operation is there, and this is the formula we're talking about. Frequency is directly proportional to the velocity. That's it. That's the frequency, that's the velocity. Yeah. So let us again discuss about the topic again. So yeah, frequency directly proportional. This is the Kármán's vortex frequency, and we'll get to know this is again a Stronghal number. This is the main formula of this particular operation. So the Kármán vortex frequency F is proportional to the velocity V. Therefore, it is possible to obtain the flow rate by measuring the Kármán vortex frequency. This is the formula. F is equal to STV divided by D. F is the Kármán vortex frequency, ST is the Stronghal number, and V is the velocity, D is the weight of the vortex shutter. And this is the weight of the vortex shutter we have seen earlier. And this is the Stronghal number. What is Stronghal number? The Stronghal number is the ratio between the vortex interval and the shutter bar width inside the pipe. This is the point A, this is the point B, this is the particular difference between ratio between the vortex interval and the shutter bar width. Yeah, this thing. So usually the vortex interval, which is denoted by L, is which is denoted by capital I, is about 6 times the shutter bar width. Usually this is 6 times. That is with approximately Stronghal number is the reciprocal value, that is around 0.17. Yeah. Again, when the Stronghal number is fixed, the velocity can be measured by counting the number of the vortices. the phenomena of the Strouhal number and how does it get implemented into the formula we've seen here. So at the end we'll get to know about, understand about what type of benefits does the vortex flow meter give to us. Like this is the mechanical construction of it. You can see this is the indicator, there's a local interface, there's a LED there, and which gives the local interface out there, and there's an amplifier inside it, remote available. So gasket is high reliability of it is present out there. So the function of the gasket is high reliability, and the body is present out there, shader bar is out there, and the hermetically sealed is out there. So this is the sensor basically. This is the sensor, and this is the solid metal out there, and the shader bar is nothing but the solid metal, and the rugged construction is very tough and rugged. There's no moving part, which is the main advantage of it. There's a full NCI rating, and this is for the 4 body, and that's all the mechanical construction of a vortex flow meter is that. And we'll jump into the why the user uses more this vortex. Vortex simplifies installation and reduces cost. That's the main thing. By improved reliability, no impulse lines to plug, freeze or leak, reduces the potential leak points. So reduced cost in line devices, it is cost effective, and smaller lines reduces maintenance, no impulse line, no periodic calibration required, can be applied in most applications where DP or phase has traditionally been used. There's a two-wire, there's application to applicable to gas, liquid, steam, where temperature range is, you can see, 450 centigrade. There is the first thing is this is the very cost efficiency, and the reduced cost is due to the no implementing impulse or no periodic calibrations, and this is required in it, and that's all. And you can see the benefits of it. The benefits are the like it can be used for digital flow signal, low install cost, and a wide range of abilities. It gives a wide range of measurement, and it has an inheritability of linear output. The output gets linear in the graph if you plot. And the low pressure drop, there is no pressure drop. Actually the pressure drop is very much low, but actually when you get the plot in a particular phenomenon, we can plot the graph, and you can see that there is a linear output. So when the output will be linear, that is the very low pressure will be in the measurement, means low pressure drop in the measurement. Okay, so this is the thing, this is the main benefit of it. And liquid, steam or gas applications can be there, and immune to density and viscosity changes. If the fluid is there, if it gets the density gets changed and viscosity also gets changed, but no effect is caused during the measurement of it. That's the main benefits of a vortex flow meter. There is a high performance benefits out there, like a high accuracy. It is a automatic gas expansion factor correction. There's a temperature compensation. There's a turn down. There is a turn down is as high as 20:1, provides accurate control over the water process conditions, and eliminates ambient temperature effect on the analogous output. Yeah, there's the main thing. And we can see the accuracy of a reading of the liquid is 0.75%, and 1% for gas and steam. And it also dramatically increases the accuracy for gas as well. We have seen in some practical experiments of it. So that's all. And at the end we'll have some discussion regarding again this topic in the next lecture, means how does we use it in a practical lab or in a practical industries. We'll understand it. So for now, that's up to